So we're going to start finish section 2.1 today. One of the things that I want to sort of make you aware of is that inside of Canvas right now, Canvas is not what I meant, WebAssign. Inside of WebAssign right now, your homework for this section does not do a very good job of proofing the limit stuff that you're doing. So make sure that you're practicing the limit definition on, I think it's at least the first 9 problems, which are simply find the derivatives or find the slope of the tangent line kind of stuff, just shy of actually finding tangent lines. I would make sure that you can practice doing that because I will ask you to actually find the slope of a tangent line with that limit definition on Friday for sure. And so I'll expect to see either the 4-step method or to see you showing it out with all the other details all combined together like I showed you the first time. So just make sure that you have practiced that by Friday. All right, so we left off last time having looked at finding the tangent line, which was this one right here, and then I just sketched for you what would look like if you looked in your calculator to verify that, and talked about what that would do in your calculator. So there are actually a few places, and I alluded to them last time that we would encounter them, where derivatives simply don't exist. And they do have a little bit to do with continuity, but not exactly. So the first discontinuity, or the first place where tangent lines don't exist is discontinuities. So discontinuities have to do with holes and jumps. And truthfully, I don't have it written down my notes, but asymptotes as well. So if you have an asymptote somewhere, or if you have a hole in the graph, or if you have a jump in the graph at that specific point, the derivative will not exist. So if you have things that look like that, or they look like this, or they look like this, not a good one, how about that? Then at those locations where that specific feature exists, the derivative does not exist. Sharp turns is another place. Now sharp turns represent continuous functions, but they have a sharp change in value. Or in direction, I should say. So we saw this on limits. Limits exist, that's fine. Continuity exists, that's fine, but derivatives don't exist. And the reason that derivatives don't exist, and this is a pretty stark example, but it's pretty easy to imagine. You could probably imagine that this is maybe a slope of, say, positive 2. And this is a slope of, say, negative 2. So there's a slope of positive 2 on the left, and there's a slope of negative 2 on the right. And so those are the tangent lines that we've been talking about. So what happens at this point where it changes from negative 2 to positive 2? Well, we define it to say that it does not exist there, okay? And then vertical tangent lines is the last one. So the vertical tangent lines we don't see occur very often, but they do come up occasionally. So a vertical tangent line happens when you have a graph that's very, very vertical at a location. And if you were to try to find the tangent line at that location, it would actually end up being a vertical tangent line. The tangent line exists. It's just that it's vertical, and the slope of vertical lines doesn't exist. All right, so if you'll remember, the slope of this, or the vertical line here would be something like x equals, I'll make up a number, 5. So this is your equation of your tangent line. But when that happens from college algebra or some algebra course you've had before, your slope does not exist. And if the slope does not exist, then the derivative does not exist because the slope is the derivative. Okay? So there is a connection, however, between continuity and differentiability. So differentiability means being able to find a derivative. So differentiability, if you know something is differentiable, it does have a derivative, then that means it has to be continuous. So being continuous is not enough to be differentiable, right? Because my second example, my third example, they were all continuous on the second and the third example, right? Those were continuous, but the derivative did not exist at some location. But if you do have the derivative, then it will be continuous. All right, so I hope you have your calculator for the next one simply because it'll be easier to describe probably from a calculator perspective, but I'll describe it too from a perspective of graphing that might be helpful. This is an interesting one because it's not an absolute value of a linear equation like we've actually done a little bit with that in class. It's an absolute value of a quadratic. So let me talk about it from the standpoint of how you can think about it from a graph point of view if you don't have a calculator or a calculator that you know how to do this feature with. This graph, if it didn't have the absolute values, x squared minus 9, I hope that you remember it's a parabola and it's crossing down here at negative 9. Do you guys remember that? Okay. So this is what the basic graph would look like if it didn't have the absolute value part. Now what the absolute value of something does is it takes everything that's negative and it flips it up and it makes it positive. So in a very real sense, this graph, from this point of view, would become a graph where it's coming down and then it has this loop up and then it comes back up from the other side of the parabola. That's the shape of it. Okay? And these locations, specifically where it's flipping direction right here and here, have to be the locations where this equation is equal to 0. So where is x squared minus 9 equal to 0? Yeah, positive and negative 3. So this is happening at negative 3 and at positive 3. So we can do that from the standpoint of this one simply because it's not too challenging because it's a parabola. But I'd like to show you how you can actually use your calculator if you were stumped on how to think about this graph. Because you do have an absolute value button in your calculator, whether you realized it's there or not. So, yeah. If you hit y equals, if you're using 283, 284, hit y equals, and if you hit the math button, it's on the left-hand column, and you go over to the num. So it's math and then num. The first one says ABS. Do you guys see it? Is anybody not seeing the ABS that I'm referring to right now? Because I'll come over and fix your calculator. Okay, if you click on that ABS, that actually does absolute values. They don't look like our absolute values. It looks like ABS in a parenthesis, right? And then you're going to say x squared minus 9, and then you end the parenthesis and it ends the absolute value. So your calculator screen, if you're doing this along with me, should now say y1 equals ABS parenthesis x squared minus 9. And most of the time, when we don't have a good reason to start somewhere else, we'll use our standard window. So you can hit zoom 6. That's the standard window. And you see the same image that we have here, right? The scale's a little bit different, but that's sort of irrelevant. Okay. Now, to the question it asks. It actually asks you to describe the x values where it is differentiable. So oftentimes, it's actually easier to describe, or at least to notice, the places where it is not differentiable. So where is this equation, this absolute value equation, not differentiable? Yeah. Yeah. So it is not differentiable at x equals negative 3 and 3. And you're right, Nick, and why? There's sharp turns, right? There are. We actually had to flip it up if we were doing it by hand. There's sharp turns. So if it's not differentiable there, then we would say it is differentiable everywhere else. So depending on what your WIBASign does, there's a couple of different ways that it might expect your notation. It might be able to allow you to say that it's differentiable and put in set notation where you say x, such that x is a real number. That looks like a little bitty e. And x does not equal 3 or negative 3. That's one notation that it might want you to use called set notation. I hope you've seen it before. If you want to use that for your homework stuffs, not homework, but your quiz stuffs, your test stuffs, you can use that for me.
Wait, called what?
What's what?
What did you say it was called?
This is called set notation, or sometimes it's called set builder notation, depending on the resource that you're using. Those curly braces designate that you're working with a set. The other way that you can do this is with interval notation. So it's differentiable, and you describe it on the intervals. So we start from the far left, negative infinity. It's differentiable all the way until we get to negative 3. And then there's a union. It's differentiable from negative 3 to 3, right? That flipped up part. And then we do a union, and then it's differentiable from 3 to infinity. And again, you should have seen that notation before as well. I'm not sure what WIBASign is going to make you use. Either one's fine with me. Does it say intervals? Okay, cool. So be prepared then inside of WIBASign anyway to use this notation. And like we said, that's interval notation. So any questions on that, either about the graph or about the notation, anything that's coming up from that you have questions about?
You said that after the on set builder notation, it's X such that X
Mhm.
is a real number.
Yeah.
How do you draw that little E thing? Is it
So
just
I'll draw it a little bit bigger, but it looks like sort of like a C with a line in the middle. That's kind of what it looks like.
Okay.
It's actually mathematical notation that means is an element of, so it's like that. That's where the E is coming from.
Okay.
So that's the notation that's in between there. Yeah, and then the R has a double bar on the left-hand side to represent the real numbers. Yes, ma'am.
What's the asterisk for?
I just marked it because somebody had said that WebAssign was having you do this. So WebAssign looks like it might be choosing this notation for you. But again, on your quizzes, exams, you can do whichever you like for me. Okay. Anything else? All right, that's it in 2.1.